Okay, welcome students. Uh, the topic for today is the binding energy of a nucleus. So last few classes we have been discussing about the basic properties of a nucleus, like the charge of a nucleus, the basic physical properties of a nucleus, the charge, the size of a nucleus, its composition. We have discussed about these basic physical properties of a nucleus. So for today, we'll be talking about the binding energy of a nucleus. So as we have discussed earlier, the nucleus is a very stable entity. It is the core of an atom in which almost all the mass of the nucleus and charge is concentrated. So it's a very stable entity. And as we have discussed, inside the nucleus or in nuclear dimensions, a special kind of a force operates, and that force we call it the strong nuclear force. It's the strong nuclear force, and this force is special in its sense. It's very strong, and it operates only in nuclear dimensions. That apart, the strong nuclear force is independent of charge. So what it basically means is that in a nucleus, which is formed from the constituents that are the nucleons, the protons and the neutrons, these protons and neutrons are held together inside the nucleus strongly by the strong nuclear force, and hence the nucleus is a very stable entity. But one point to note here is that different nuclei have different stability. So it's not that all of them are equally stable. So we know about nuclei which are unstable and they spontaneously disintegrate through the process of radioactivity till they attain stability. So how to compare the stability of different nuclei? So we need a parameter which can distinguish or which can classify the stability of the different nuclei or the nuclei of different elements. So here comes the question of what is known as binding energy. So what is this binding energy? From the name itself, we can make out binding energy. It simply means the energy with which a nucleus is bonded together. The energy with which the constituents of a nucleus, they are held together to form the nucleus. So what we'll be trying to do is, we'll be trying to find out a mathematical expression for that, for the binding energy. So before that, we can talk about the definition of binding energy. So what binding energy basically means is there are two alternative definitions. One is the amount of energy. You can talk about it as or define it as the amount of energy which is needed to break down or to break up a nucleus into its individual constituents. Break up a nucleus completely into its individual constituents. So as we have talked about, a nucleus is composed of protons and neutrons. So if I have a nucleus having a certain number of protons and neutrons, so for that nucleus, the binding energy will be the total amount of energy that we'll need to supply to the nucleus so that we can break it up into its individual constituents. So this is one definition of binding energy. Alternatively, also it has been found that when a nucleus is formed from its constituents, that is from the protons and the neutrons, the total mass of the nucleus that is formed is not equal to the sum total of the masses of the individual protons and neutrons. We'll talk about it more. It simply means that when a nucleus is formed from its constituent protons and neutrons, a certain amount of mass is lost in the process. So we just can't say that the mass disappears. What happens is the amount of mass that is lost in the process of formation of a nucleus is converted into energy and released in the process. So basically it means that when a nucleus is formed from its constituent protons and neutrons, a certain amount of mass is converted into energy and released in the process. So for that particular nucleus, that amount of energy which is released is the binding energy of the nucleus. So these two analogous definitions for binding energy. So we can also define the binding energy as the amount of energy which is released, during the formation of a nucleus. So these are two alternative definitions. One is the amount of energy needed to be supplied to a nucleus to break it up into each individual constituents, or in other words, is the amount of energy released during the formation of a nucleus. So if I form a nucleus from its constituents and a certain amount of energy is released, so the nucleus becomes stable, it's a stable entity. So to break that nucleus into each individual constituents, I'll have to supply the same amount of energy to break it up again. So these two values are equivalent, they are equal. So as we always tell in physics or in science as such, we need quantitative measurements. So we just can't say that one nucleus is more stable and the other is less stable. So to compare them, we need quantitative measurements. So we need a quantitative measurement for the binding energy of a nucleus also. And hence we need a mathematical expression. So let's try to find out a mathematical expression for the binding energy of a nucleus. So let us say we have a nucleus A, X, Z. This is the common notation that we follow for a nucleus, where A is the mass number of the nucleus and Z is the atomic number. X is the symbol of the element. For example, let me say I have a nucleus 12C6, I denote it like this. So this is the nucleus for the element carbon. 12 is the mass number and 6 is its atomic number. So here we have, for this nucleus AXZ, we have, let me write it here, A as the total number of nucleons. Total number of nucleons in the nucleus. That means the total number of protons and neutrons in the nucleus. Z is the atomic number. It means it's the total number of protons inside the nucleus. So hence from this we can find out that A minus of Z will be the number of neutrons inside the nucleus. So can we find out an expression for the binding energy of this nucleus? So what we have discussed is that during the formation of a nucleus, a certain amount of mass is lost in the process. So for the formation of this nucleus, let us see what is the amount of mass lost. That mass lost is also called the mass defect of the nucleus. So for this nucleus, we have Z protons. So let Mp be the mass of the protons. Let Mp be the mass of the protons. Similarly, let Mn be the mass of the neutrons. So for this case, we have the total mass of the constituents, that is Z Mp plus of A minus of Z Mn. So Z protons and A minus Z neutrons comes together to form the nucleus AXZ. So the resultant nucleus, let M nuclei be the mass of the resultant nucleus. Mass of the nucleus of AXZ. So what we are saying here is that the total mass of the constituents forming the nucleus is not equal to the total mass of the resultant nucleus. That means, in this case, Zmp plus A minus of Zmn is not equal to the mass of the resultant nucleus. So that's what simply we can say. I was telling you in the earlier class also. In nuclear physics, 2 plus 2 is not equal to 4. Don't take it literally. It's just an example I am taking to prove that in the formation of the nucleus, the sum together of the constituents of the nucleus is not equal to the mass of the resultant nucleus that is formed. So this difference of mass, what is usually found is that this sum is greater than the mass of the resultant nucleus that is formed, is greater than the resultant nucleus. So this difference in mass is called the mass defect for this nucleus. So this mass defect is denoted by a symbol del m. So that is equal to, for this nucleus, it will be equal to ZMP plus A minus ZMN minus the mass of the resultant nucleus that is formed. So this difference in mass is called the mass defect. So what is binding energy then? For this nucleus, the binding energy will be equal to the energy equivalent of this mass defect. So what comes to our rescue is that the amount of mass which is apparently lost during the process of formation of the nucleus is converted into energy and released. This conversion takes place according to Einstein's mass energy relationship. So for this nucleus then, the binding energy will be equal to the energy equivalent of this mass defect. So we get an expression for the binding energy which can be written as EB is equal to ZMP plus A minus ZMN minus of M nucleus into C square. Right? So, for this nucleus AXZ, the binding energy expression will be EB is equal to ZMP plus A minus ZMN minus M nucleus, where M nucleus is the mass of the resultant nucleus into C square. So, this gives us an expression using which we can find a quantity, we can have a quantitative measure of the binding energy of any nuclei. But here, to do this calculation, we need the mass of the nucleus. Now, as we already discussed, it's very difficult to find out or measure the mass of a nucleus as such. So, what is usually done is that we measure the mass of the atom of this particular element, then we subtract the mass of the electrons and we get the nuclear mass. So we can write this expression in terms of the atomic mass. So the binding energy expression easily can be converted into an expression in terms of the atomic mass just by adding here MP. So in any atom which is neutral, the number of protons is equal to the number of electrons. So if there are Z protons, there will be Z electrons. So we just add the mass of the electrons here plus add and subtract rather. So A minus Z Mn, then minus, we put mass of the nucleus. As we have added Z times the mass of the electrons, we will subtract it Z times the mass of electrons here into C square. So minus and plus makes it minus, and this is plus ZME, this is minus ZME, so they cancel out. So this is what mass of a proton plus mass of an electron is nothing but the mass of a hydrogen atom. So this can be written as, the binding energy expression can be written as, so Z times the mass of a hydrogen atom now, Mp plus Me we put it as Mh, the mass of a hydrogen atom, plus E minus Z Mn, this is the mass of a neutron, minus N nucleus, the mass of the nucleus, plus it has Z electrons, that times the mass of an electron, that gives me the atomic mass. So this expression is in terms of the atomic mass. So these are two alternative expressions. The binding energy expression in terms of the nuclear mass and the binding energy expression for a nucleus AXZ in terms of the mass of a hydrogen atom and the atomic mass. So this becomes easier because we can measure the mass, atomic mass easily. We can measure using different mass spectrographs, we can measure the atomic mass of different elements. So using this expression, we can find out the binding energy of the nuclei of different elements. So actually we'll try to calculate the binding energy of the nuclei of different elements. We'll do some problems on this, and this expression becomes very, very important. Okay, the next thing we'll talk about is the binding energy per nucleon of a nucleus. Why it is important? If we want to study the relative stability of different nuclei, it's not enough just to compare the total binding energy of the different nuclei. Why does this binding energy arise in a nucleus in the first place? It arises because of the strong internucleon interactions due to the strong nuclear force which is holding together the nucleons in the nucleus. So obviously, more the number of nucleons in the nucleus, that is, higher the mass number, the total number of internucleon bonds will be more, and hence the sum total of the binding energy of the nucleus will be more. So that has been experimentally observed also. Higher the mass number, more is the total binding energy of the nucleus. But does it mean that those heavier nuclei are more stable than lighter nucleus? Rather, it's contrary to that. We know that a uranium nucleus is comparatively much unstable compared to a helium nucleus, which is one of the most stable entities, stable nuclei. So how can we compare the relative stability of different nuclei? So just comparing the values of the binding energy EB, total binding energy EB, does not give me a true picture. So what we need to do is, we need to compare the binding energy per nucleon of the nucleus. So if I have a nucleus having a mass number E, what I need to find is the binding energy per nucleon. We call it Fb, usually we denote it Fb, that is equal to the total binding energy divided by the mass number of a nucleus. A rough analogy that I usually talk about, we can say, suppose you have 100 rupees with you and you divide it among, say, 5 persons. So per head. And another case, you have 200 rupees, but you divide it among 10 persons. So which one is in a more advantageous position? 100 rupees. Okay, we have to increase the number. Let me say 100 rupees I am dividing among 5 persons. So 100 rupees if I divide among 5, per head we are getting 20 rupees. Let me say 200 rupees I am dividing among 20 people. So per head I am getting 10 rupees. So if you just see the amount of money which is being distributed, 100 rupees and here it is 200 rupees. You may have a tendency to think that this is a better perspective, better position. But what happens is, per head you are getting 20. But in this case, 200 among 20, but you are dividing among 20, you are getting 10 rupees per head. So similar is the case here. In the case of binding energy, we have to see the total number of nucleons which is involved in the nucleus to give this binding energy. So when we calculate the binding energy per nucleon, that gives us a true picture of the stability of different nuclei. So we need to compare not the total binding energy of the different nucleus, but we need to compare the binding energy per nucleon of a nucleus. Analogous to this, another term is also there, we call it the packing fraction. So Another term is there which is called the packing fraction. Packing fraction is nothing but the mass defect per nucleon. So mass defect into C square gives us the binding energy. So these two are analogous to one another. They are related to one. They just a term C square is you have to add it over there. This is called the packing fraction, and in some books you will see this. This is called the binding fraction. So we are calling it the binding energy per nucleon of a nucleus. So it simply means that if I have to compare the stability of the nuclei of different element, I will compare the binding energy per nucleon of the different nuclei. Okay, as we talked about, we need to compare the binding energy per nucleon for different nuclei. That means the binding energy of the nuclei varies with mass number, and hence the binding energy per nucleon of different nuclei it varies with mass number. So this plot it shows us a variation of the binding energy per nucleon of different nuclei with mass number. So along the y-axis we are plotting the binding energy per nucleon of the nucleus Fb in units of mega electron volt MeV, and along the x-axis it is A. So what is observed is that for all mass numbers, this is important, for all mass numbers or rather for all nuclei, the binding energy is positive. That simply means that for all nuclei, we need to supply some amount of energy to break it up. That means the nucleus is a, what to say, it's a stable entity. Then, for lower mass numbers, till around 60 to 70, there is a sharp rise in the binding energy per nucleon. The rise is very sharp. Of course, there is an erratic variation. Erratic in a sense, there are small peaks that can be observed. So these peaks they occur for mass number corresponding to 4, 8, 12, etc. So mass number corresponding to 4 means this corresponds to the helium nucleus. So helium nucleus is a very stable entity. 8 is oxygen, 12 is carbon. So these nuclei has comparatively very high binding energy per nucleon compared to the others. So it shows the stability of the alpha particle structure. Alpha particle structure means the helium nucleus. So these small peaks are seen here, erratic variation, but the rise is quite sharp. Till it reaches the maximum point, it corresponds to iron 56 nucleus. So iron 56 nucleus has the maximum binding energy per nucleon among all the elements. Beyond that, we see that from around 40 onwards, on an average, we can say that the binding energy is almost saturated at a value of around 8 MeV. So this saturation it shows the saturation property of nuclear forces or the strong nuclear force. So when we discuss about nuclear forces, we'll talk more about it. So now the characteristics of the variation of binding energy per nucleon. First important point to remember is that all the nuclei they have a positive binding energy. Second point, as the mass number increases, for lesser mass numbers, there is a steep rise in binding energy per nucleon with mass number till it reaches a maximum at iron 56. That's the second point. Third point, for lesser mass numbers, there is an erratic variation of the binding energy per nucleon with mass numbers. Small peaks observed at mass numbers corresponding to 4, 8, 12, etc. This shows the stability of the alpha particle structure. Third point, fourth, from mass number greater than around A is equal to 40, the binding energy per nucleon is almost constant. On an average, you can say it's almost constant. This shows the saturation property of nuclear forces, as we talked about. Also, this curve can explain the energy released during fission and fusion process. How it can explain the energy released during fission and fusion process? What is fission? Fission is the breaking up of a heavier nuclei. Let me say uranium 235, it will fall somewhere here. So breaking up of a uranium nucleus, it will form barium and krypton. Barium is around 92, krypton 141. Somewhere it will come down in this scale. So there will be somewhere here. So uranium lies here. So in the process, what happens? Uranium has lesser binding energy per nucleon. When it breaks up into its constituents, the constituent or the fission products that are formed, barium and krypton, they have higher binding energy per nucleon. That means what? During the process of breaking up of a heavier uranium nucleus, an amount of energy is released. Hence, the resultant daughter nuclei or the fission products, they are comparatively stable or they have higher binding energy per nucleon than the original nucleus which is undergoing fission. So, this curve itself can explain why energy is released in a fission process. Again, I'll tell you, heavier nucleus, lesser binding energy per nucleon, it undergoes fission. During the process, fission products are formed. The resultant nuclei of the fission, they have higher binding energy per nucleon. That means the resultant nuclei or the fission products, they have higher binding energy per nucleon, hence they are more stable. That simply means during the breaking up of the fission, during the breaking up of a heavier nucleus in the fission process, energy is released so that the products are more stable. Other way around, fusion, same thing happens. Lighter nuclei, they combine together to form heavier nuclei. Let me say 4 hydrogen, hydrogen will be A is 1, somewhere here. 4 hydrogen comes together to form a helium. So helium comes somewhere here, upper. So what is observed in this process also again, when fusion takes place, lighter nuclei, they combine to form a heavier nucleus, the binding energy per nucleon of the resultant nucleus is more. Same thing as in the case of fission, the products, they have higher binding energy per nucleon. In the fusion process, the resultant nucleus of fusion has higher binding energy per nucleon than the nuclei which are undergoing fusion to form the product. Hence, in this case also, energy is released in the process. Okay, so let's see how actually the binding energy of a nucleus can be calculated. So I'm taking a problem from this book. So we have to calculate the binding energy of an alpha particle and express it in MeV and joules. Or simply we'll calculate the binding energy of an alpha particle. So given that the mass of a proton is equal to 1.00758 AMU, atomic mass unit, the mass of a neutron, that is equal to 1.00897 U, and the mass of a helium nucleus, that is the alpha particle, that is equal to 4.0028 U. So we need to calculate the binding energy of this nucleus. So what we need to do is, basically we need to find out the mass defect for this nucleus. So the binding energy expression for this EB, we have the expression that is equal to Z of MP plus A minus Z Mn minus the mass of the nucleus into c square. So these masses are given in terms of atomic mass unit. So in this case, for the alpha particle, Z is equal to 2. So obviously A minus of Z also is equal to 2. So 2 protons and 2 neutrons come together to form the nucleus. So this expression we can write in terms of the mass defects. It is del m c squared. So first we need to find out the mass defect for this nucleus. So we can find out, so del m for the alpha particle will be del m is equal to 2 times the mass of a proton plus 2 times the mass of a neutron minus the mass of the alpha particle. So we can do this calculation, just put down the values. So you will get del m. So you will get del m in units of atomic mass units, right? So we just can't directly write del m into c square because that will give us in energy units in terms of joules. So there del m needs to be in kilograms. So we have a conversion from atomic mass unit to MeV directly. So we use the conversion 1 atomic mass unit or 1 U into c square, that is equal to 931.49 MeV. So directly we can use this conversion. You can also try to do this calculation. What is 1 U? 1 U is nothing but the mass, 1/12 of the mass of a carbon-12 atom. We can actually do this calculation and see whether it gives us 931.49 MeV. So how it can be done? 1 U is nothing but equal to the 1/12 of the mass of a carbon-12 atom. So what is the mass of a carbon-12 atom? We can find out in kilograms. So how we can find out? We know that 1 mole of carbon-12 weighs 12 grams. So this simply means 1 mole contains Avogadro's number of atoms, 6.023 into 10 to the power 23 atoms of carbon-12 weighs 12 into 10 to the power minus 3 kilograms. So 6.023 into 10 to the power 23 atoms of carbon-12 weighs 12 into 10 to the power minus 3 kilograms. So from this we can find out the mass of one atom of carbon-12, and hence we can find out the mass of 1/12 of the mass of a carbon-12 atom. So that gives us 1 U, 1 atomic mass unit. 1 atomic mass unit in units of kilogram. So multiplied by c square. So this 1 U you will get in kilograms. This 1 U you can multiply it by c square. In SI units you will get in terms of joule. So joule we can convert it into electron volt and mega electron volt. So 1.6 into 10 to the power minus 19 joule is equal to 1 electron volt. So mega electron volt is 10 to the power 6 electron volt. So 1 U can be expressed in terms of mega electron volt. And after doing the calculations, this is the conversion we'll be using. 1 U into c square directly gives us 931.49 MeV. So in this case, to find out the mass defect, or find out the binding energy of an alpha particle, we need to find out the mass defect for the alpha particle. Then whatever value we get, we have to convert it into mega electron volt, or we can convert it into joules also. So after doing the calculations, we get the mass defect for the alpha particle to be equal to 0.0293 with these values that we have written down, U. So we know that 1 U into c square is 931.49 MeV. Therefore, the binding energy of the alpha particle, or we write it as EB, the binding energy of the alpha particle is del m into c square, that is equal to 0.0293 U into C square. Now we know 1 U into C square is equal to 931.49 MeV. Therefore, the binding energy of the alpha particle is nothing but 0.0293 into 931.49 MeV. So the final value that we get is around 27.29 MeV. So if you do this calculation for the alpha particle, we get the total binding energy to be equal to around 27.49 MeV, mega electron volt, and hence the binding energy per nucleon for the alpha particle, the binding energy per nucleon for the alpha particle, that is equal to EV by 4. 4 nucleons, 6.8 something MeV. So this is the binding energy per nucleon for the alpha particle. So that is all for this lecture. We'll continue from here on in the next lecture.